Dear friends, welcome to another video pertaining to the gravity method. And here we extend the previous theory so that we can go beyond point masses and develop an understanding how spatially distributed subsurface structures will appear in gravity datasets. In order to do this, we will develop some models which allow us to make predictions. This means, given a known subsurface structure at a given depth and with a given shape and a given density contrast, what will be the gravity anomaly that I measure at the surface? And we will call this step forward modeling. We will also turn this question around, meaning if I have measured a certain gravity anomaly, what is the subsurface structure that goes along with this observation? And we will call this way of asking the question the inverse way. And we will find that the inverse way is, first of all, much harder than the forward way, but more critically, there are typically multiple explanations for any given set of observations. And we will call this the principle of equivalence, and this principle is inherent in all applied geophysical methods. Okay, before I go into those 3 points, I will clean up a little riddle that I left you with in the last video, and this pertains to these units which are called milligal. Gal refers to Galileo, who also famously contributed to the theory of gravitation, but in essence it is simply a scaled version of acceleration. 1 gal is 0.01 meters per second squared, and a milligal is correspondingly much smaller. In fact, it is about 1/1,000,000th of the mean acceleration at the Earth's surface. And this gives you an impression about the required sensitivities and about the qualities of the corrections that need to be applied in order to get such a detailed image of the subsurface. Okay, so far we have treated all objects as point masses, meaning we neglected any spatial extent as seen here and consolidated all the mass in the center. And now we would like to relax this assumption. For example, we would like to ask, what is the gravitational field inside and out of a spherical shell? And I would like to argue that there's really only one answer which is immediately intuitive, and that is that the gravitational pull at the center here will be 0. And the argument goes as follows. If I am situated at the center, then all point masses which make up the spherical shell exert a gravitational pull. However, for each point mass on one side, I will find a point mass on the other side which pulls in the exactly opposite direction, so the net effect will be 0. However, once I move away from the center, I find the situation is less clear, and the reason is that I now need to account for this 1/r² dependency. For example, if I'm located close to the rim, then on the one hand there is point masses over here to which I am very close, so their gravitational pull will be comparatively strong. However, on the entire other side, many more point masses pull in the other direction. They're weaker, but more. And as it turns out, the net gravitational effect inside a spherical shell cancels everywhere. So everywhere in this shell, I wouldn't feel any gravitational pull. So how about if I'm located outside the sphere? Here, clearly, I will feel a gravitational pull because all of those point masses act as an attractor. But to calculate the exact magnitude of this spatially extended target is actually not very straightforward, and I do spare you the mathematical details here. The nice result is that we can replace a spherical shell with an equivalent point mass located at the center. Equivalent point mass means that I consolidate all the weight of the masses which are in the spherical shell in the center. And this is nice because we can now apply the theory of a point mass that we have developed previously. Okay, a spherical shell is still a very idealized target that you will never encounter in nature. However, this concept is already useful if you would like to calculate, for example, the gravitational field inside the Earth. And that again would be important if you would like to drive a model of, for example, mantle convection. Okay, so Newton's shell theorem, again Newton who nicely solved that for us, summarized, is that the field outside a shell is the same as the one from an equivalent point mass located at the shell center. The field inside a shell is zero everywhere. And you can apply those findings in the exercises. Knowing the shell theorem is useful in order to develop our first model of a spatially extended subsurface structure, and for simplicity we will assume, surprise surprise, a spherical cave in the subsurface. Thanks to the shell theorem, we can replace this cave with an equivalent point mass, and this point mass is determined by the geometry of the cave and the density contrast relative to the surrounding. And we will place this equivalent point mass at the cave's center. The question that you will need to answer in the exercises is, what is the expected vertical component of the gravitational pull exerted by the target? And why only the vertical component? Well, gravimeters typically only measure the vertical component, and your DIY smartphone's freefall gravimeter from the previous exercise is no exception to this. Remember, we only consider the trajectory of our test mass along one of the three possible axes, and correspondingly, we only detect the vertical projection of this vector g. For determining the mean density of the Earth, this wasn't really an issue, but here it matters because of the acquisition geometry relative to our target. And we should take this further. One measurement will tell you very little about the nature of our target, and therefore we need to collect multiple measurements along a profile. And so what you now need to predict with your first forward model is, what is the expected vertical gravity anomaly Gz as a function of the horizontal distance? And here we choose the coordinate system so that the target is located at the profile's center. And 3 points can be identified right away. Far away from the target, on either side of this graph, the expected gravity anomaly must be 0, and this is because of the 1/r² dependency. And correspondingly, closest to the target, the magnitude of the expected anomaly must be largest, and this should be unsurprising at this stage. However, what is probably less clear is what kind of dependency to expect between those known points. And the results of your exercises will be your first forward model, which applies to a spherical target in the subsurface. And even though this is still heavily idealized, it is quite useful because it allows you to investigate sensitivities. For example, what signal magnitude can you expect for a medium-sized cave located tens of meters below the surface in a karst area? Will you be able to detect this effect with your DIY smartphone gravimeter? And if not, what sensitivities are required? These kind of back-of-the-envelope calculations are very important for designing a geophysical survey so that you can go into the field with reasonable expectations and, more importantly, with adequate instrumentation. Well, what about more arbitrary structures such as this one? At least conceptually, we can subdivide every structure into individual point masses. And all of these point masses will exert a gravitational pull towards the sensor that we have located at the surface, and the net effect will be additive and is represented by a summation over the many individual elements which are required to describe this particular shape. And note that for each of those point masses, for each of those elements, we need to include an individual distance Ri relative to our sensor. And in analogy to the previous cases, we don't only need to calculate this summation for one location, but for multiple locations so that we arrive again at a profiling solution. Occasionally, it is useful to replace this discrete summation with a more continuous integration, and this then may involve a, let's say, spatially variable density. And there's not a solution to this kind of triple integral in the most general sense. However, for a number of symmetrical cases, this integral can be solved. One example would be a horizontal plane with a finite thickness extending laterally to infinity. And we will call this solution the boogie plate solution, and we will need this later on for interpreting gravity anomalies across the globe. Another solution that exists is that for a prism. The formulas describing the gravitational effect of such a shape are not particularly appealing, but they certainly can be handled. And more specifically, they can be coded into some kind of programming language, and this only requires, I would argue, moderate programming experience. And you don't even need to understand all the details here, but the calculation requires the density contrast as an input, and this really shouldn't come as a surprise at this stage. And it also requires the coordinates at the edges of the prism, meaning we need to know where the prism is located relative to our sensor. And this is all the information required, and the rest is solving the integration shown in the previous slides, which fortunately has already been solved by others. And so to illustrate this specific example, I located a prism at about 1 kilometer depth, and I assigned a density contrast. And I don't go into much detail here because this is what you will do in the exercises, but in principle the predicted anomaly shown here on the top is as expected, with negligible anomaly contributions far away from the target and a maximum in magnitude where the target is closest. However, the functional dependency between those points that we see here is somewhat different from that of an equivalent point mass. And with these two forward models, the numerical forward model here and the one from a point mass that we covered previously, you can already differentiate between these two different cases, and really nothing stops you from using multiple prisms in order to prescribe more complicated structures. In fact, I urge you to do this in the exercises. And once you start using multiple prisms, you can explore the principle of equivalence by finding different arrangements in the subsurface with different locations and different density contrasts, which would result in virtually the same gravity anomaly detected at the surface. And to frame this in a more general sense, if we know the model parameters of the forward model, and here this would correspond to a vector including the shape and the location and the density contrast of that prism, then we can predict the expected gravity anomaly. We know this forward modeling step by now. However, remember, typically we encounter this problem in the other direction. What we do is that we collect observations and we have absolutely no idea about the subsurface structure and its model parameters. This is actually the whole point. We go there because we don't know the subsurface. So what we need to do is that we combine our observations with the forward model in a way that our field observations and model predictions fit. In a simple way, we could, for example, systematically vary the parameters of our forward model by changing the location and the density contrast until the predictions of the forward model match our observations. And this can be a pretty cumbersome job, and there's definitely smarter methods of how this can be done, and we call these methods inverse modeling, and this will be covered in more advanced classes here in Tübingen at the master's level. Once you find such a good set of model parameters, this will very much substantiate the interpretation about the subsurface structure. The principle of equivalence is not a showstopper here, because many solutions which would theoretically be possible can be rejected with additional knowledge from the geological context of the specific setting that you're in. Okay, after all of this, we can summarize this video with some keywords. You understand that gravity profiling is the way to go to visualize anomalies caused by various subsurface structures which differentiate themselves in terms of a density contrast. You understand the principle and use of forward models, and you know some forward models, and you also understand that forward models and observations can be paired in a framework that we call inverse modeling. And a big caveat, but not a showstopper, in all of these methods is the principle of equivalence, which we have just explained. What remains to be done is that we move away from this simplistic setting of sensor and one isolated target with a given shape. And we need to move to more realistic settings, which include all sorts of camouflaging effects, such as Earth's rotation or tides and the surrounding terrain, and so on and so on. And we will do this in the videos that follow. Thanks for watching this video, and goodbye.